Hey, I'm Russell. So today I want to talk about the paper Quantum Algorithms for Solvable Groups. It is by John Waters, published in Stock 2001. So when we say quantum algorithms for solvable groups, we mainly mean a group order finding algorithm. So what we want to do is to find the order of a solvable group G when we are given this group G. So what do we mean by given? Well, so in this context, we mean that we are given a generating set which consists of the elements G1 up to Gm, and they are, let's say, represented by n-bit strings. And we are also given a group operation circuit, which we denote by UG. So classically, this circuit takes as input two elements and just multiply them together. And quantumly, we can write UG acting on the quantum states G and H, and the result would be G and G times H. So we need to have G there because quantum operations need to be reversible. Okay, so what does this algorithm have to do with cryptographers? So at least for me, understanding the construction of this algorithm may help us understand how we can possibly construct post-quantum secure hidden order groups. So as you may have already guessed, if such a thing exists, then such a group better be non-solvable, right? Because we have, as we will see right now, we will have a quantum algorithm for finding group orders for solvable groups. So what is a solvable group then? To explain this, let me begin by explaining normal subgroups. So let H be a subgroup of G. H is said to be normal if for any group element G in big G, we have G times H equals H times G. Okay, so that means if I take any element small h in big H and I left multiply G to it, then I get some other element H prime times G. And this H prime is in big H also. And if this happens, we write H, a small triangle, and then G, denoting that H is a normal subgroup of G. We also need another concept called the commutators. So the commutator can be defined by two group elements G and H, and it is just the group element computed by G inverse H inverse times G times H. So now, if we have two subgroups, H and K of G, then we can generate a so-called commutator subgroup, bracket H and K, by considering the group that is generated by all commutators between the elements H and K, where H comes from the group H and K comes from the group K. So given this notion, we have a well-known result that the commutator between G and G itself is the normal subgroup of G. So next we need the concept of a derived series. So the derived series of G is a sequence of normal subgroups denoted by G to the L, G to the L minus 1 up to G to the 0, which is defined as G, where G to the I plus 1 is just the commutator subgroup generated by Gi and Gi itself. So now we can finally define what solvability means. So G is solvable if there exists some positive integer L, finite, that G to the L is just a trivial group, so it consists of just the identity element. And if this thing happens, then we have a result saying that the quotient group of gi over gi plus 1 is abelian. Alternatively, we have the other definition here, which will be more convenient for us. So here we say that G is solvable if there exists m group elements, G1 up to Gm, such that we have the following sequence of normal subgroups: H0, H1 up to Hm, which is G, such that Hj is generated by the first j elements, G1 up to Gj. And because the difference between Hj plus 1 and Hj is just one group element, so we have that the quotient group of Hj plus 1 over Hj is cyclic, and this will be important for us later on. There is also an interesting result saying that there exists a Monte Carlo polynomial time algorithm which inputs any generating set of G and outputs such G1 up to Gm, which satisfies the definition we defined above. If G is solvable, of course, right? So this Monte Carlo algorithm can find us G1 up to Gm so that Xj is generated by G1 up to Gj. In case you don't know, a Monte Carlo algorithm is just an algorithm with bounded error. Okay, so once we have defined this sequence of normal subgroups, H0 up to Hm, we can define the order of the quotient group, Hj over Hj minus 1. Yep, the order of this quotient group to be Rj. And we say that we also call this the order of the element Gj with respect to the group Hj minus 1. Or in other words, Rj is the smallest positive integer such that Gj to the Rj is inside Hj minus 1. So the way to think about it is that Gj originally is not in the group Hj minus 1, but in Hj. And we multiply G to itself multiple times until it collapses into Hj minus 1. So this will always happen because Hj minus 1 is a group, and eventually Gj will go to the identity element. And but it may go to Hj minus 1 sooner than this. Okay, so from now on, I assume that you are already familiar with the notation of quantum computation. So to begin, let me define this notation here. So the quantum state of big H is just the superposition of all elements in H. And for this talk, I don't bother writing down the coefficients of quantum states. So you may find that the probability don't add up to 1, but we can always normalize them to 1. So let me remind you a main ingredient of the algorithms, which is the quantum Fourier transform, or QFT. So for each integer n, we can define a QFT for n, denoted by, well, QFT subscript n, which maps this superposition of quantum states into this other state. So it takes the superposition of A and maps it with uniform distribution and maps it to the superposition of B, each with probability omega n to the power AB, where omega n is a primitive root, nth root of unity. So in matrix form, we can write QFT_n like so, where the ijth entry is just omega n to the power ij, where ij ranges from 0 to n minus 1. given these tools, we are now ready to present the group order finding algorithm. The algorithm will be split into two parts, so two sub-algorithms, algorithm 1 and 2. And I will first present algorithm 1. So algorithm 1 does the following. Given some normal subgroup H of G and some element G in big G, as well as the superposition H on H, this algorithm finds the order of G with respect to H, and we call this value R. So as usual, we prepare some quantum states, and in this case we prepare the superposition of A, where A is in Zn, for some large enough n, concatenated by the superposition of H. Then we apply the group operation circuit, which left multiplies the value G to the A to the state H. And then we apply the inverse quantum Fourier transform to the state A, which results in the state B with probability omega n to the power negative AB. And then as the last step, we measure these two states, which gives us a tuple y and G to the xh for some y, some x, and some h, with a probability that is proportional to the sum of omega n to the power negative ay, where a consists of, so a runs through all values that is congruent to x modulo r, where x is this exponent right here, and r is the order of G with respect to h. So since we know that A is congruent to x modulo r, we can write A as x plus qr for some q. So plugging this into the probability, we get the summation of omega n to the power negative x plus qr times y, where q ranges from 0 up to n over r. And here notice that we can move the value omega n to the power negative xy out, because it's a constant and it will normalize to 1. And so we end up with something proportional to the sum of omega n to the power negative q times ry. So here, note that our purpose is to find this value r, and we want some way to extract r out from this expression. So now we notice that if ry is close to 0 modulo n, then this sum is pretty large. On the other hand, if ry is large, so not close to n, then this sum, because the exponent is negative, so this sum would be small. Therefore, with quite a high probability, we will observe some ry which is close to a multiple of n. Or in other words, y over n would be close to t over r for some value t. And then using some tricks which Albrecht should have talked about already, we can extract this value r with some probability. And then by repetition we can amplify this probability and obtain r with with overwhelming probability. So now let me present the next ingredient, which is algorithm 2. This algorithm starts from a number of copies, let's say L, L copies of the superposition H, and then some element G of big G, as well as the order of G with respect to H, which, for example, can be found using algorithm 1. And then algorithm 2 produces L-1 copies of the group generated by G multiplied to H. Like so. Okay, so as usual, we prepare some quantum states. So in this case, we prepare the superposition of some AI where AI is in ZR, where we record that R is the order of G with respect to H. And we have this quantum state concatenated with the superposition H, like so. And we will prepare L copies of this, and for the ith copy, we call this part of the quantum state the register AI, and this part the register Ri. Next, we apply the group operation circuit to Ri, which results in this state, where we have a superposition over OAI concatenated with G to the power AI times the superposition of H. And then we apply the quantum Fourier transform on the register AI, which results in this state. So next, we will measure the register A1 up to AL, which will give us some values Y1 up to YL, corresponding to B1 up to BL. So now we have that with some non-negligible probability, there is some K in 1 to L such that YK is co-prime to R, or GCD of YK and R is 1. Also note that when we measure A1 to up to AL, the registers R1 up to RL collapse to this expression here. So we have Ri collapses to psi I, which equals to this expression. So remember that we started with some copies of H, and we would like to produce some copies of the group generated by G times H. And so the idea here is to use one of the psi I, in this case psi k, to correct the other psi I, so that the state psi I becomes the desired superposition. To do this, let us examine the operator denoted by m subscript g to the power j times h for some element h in big H. So this is not a valid quantum operation because it is irreversible, but we will just analyze what its effect formally, and then later we will apply it in a legit quantum operation. Okay, so let us examine what happens when we apply this operator m subscript g to the power j times h to the state psi k. So what this operator does is just to multiply the value g to the j times h to whatever is stored in psi k. So when we do this, recall that psi k is the following sum over all g to the power akh with probability omega r to the power akyk. And when we now left multiply g to the j times h, we end up in this state. So now, because H is a normal subgroup, so we have GH equals HG, and therefore this H and this G to the AK here commutes. And therefore we can move H to the right hand side and it will be absorbed into H, big H. So we end up with this expression here. And then by changing the variable from AK to AK plus J, we end up in this expression. So now we can factor omega r to the power negative j yk out and obtain omega r to the power negative j yk times psi k. So that means this operator m subscript blah blah here, or rather the state psi k is an eigenvector of this operator with eigenvalue omega r to the power negative j yk. So now for the next step, let us define zi, which is just yi times yk inverse modulo r, and yk inverse modulo r exists because we have yk and r co-prime to each other. Okay, so now for the next step, we will multiply whatever is in Ri to the power Zi to Rk. And I denote this by Ug to the power Zi. So when we do this, we have the state Ri here, and then the value in Ri, which is g to the power ai times some h in superposition, will raised to the power zi will be multiplied to psi k using this m operator that we defined before. And then due to the analysis above, we know that psi k is an eigenvector of this operator with eigenvalue omega r to the power negative ai zi. Note that we have substituted j with ai zi and yk. So because of how zi is defined, which is yi times yk inverse modulo r, this aiyi and this aiziyk cancel out and it becomes 0 modulo r. And therefore we are left with the superposition of g to the ai times h concatenated with psi k. So now note that this thing is nothing but the superposition of all elements in the group generated by g times the group h. So then we are done by just discarding this extra state. Now that we have algorithm 1 and 2, we can put them together in the following way to find the order of g. So first of all, we use the Monte Carlo algorithm that we explained before to find out all these normal subgroups, h0, h1 up to hm, which is g. And then we prepare many copies, well, polynomially many copies of h0, which is just a trivial group. And then we enter the following for loop. So for each j in M, we use some copies of hj minus 1, the previous group, to compute the order of gj with respect to hj minus 1 using algorithm 1. And then we use one copy of xj minus 1 to convert all the remaining copies of xj minus 1 to copies of xj. So after running this loop from j equals 1 to m, we end up with R1 up to Rm, and the group order is just the product of all these Rj's. So as a final note, it seems that even if H0 is not a trivial group, but some small group which we can brute force to find this order, and assuming that the later subgroups are all have cyclic factor groups, then we can apply the same algorithm to find the order of G. So yeah, thanks. This is the end of the presentation.